Welcome everyone to the second week of the Chromatic Nullstellensatz Seminar. So as we had decided, so the first few weeks we are dealing with some basic chromatic stuff. So today's talk is supposed to be so today the subject of today's talk is Morava K-theories, complex and Morava K-theories, and today's speaker is Grigory Taroyan from University of Toronto. So Grigory, please take it away.
Okay, thank you. Okay, so I'm actually not sure that we will arrive to Morava's case theory today, but I wanted to start by discussing some very basic things about formal groups and stuff like that. So we start off with the usual thing that we have the cobordism-ring, complex cobordism-ring of a point, which is isomorphic to Lazar ring, meaning that it is a ring of formal power series. Ring of formal power series in countably many variables, with degree of bi being 2i. Then the fact is that this ring is universal, meaning that if we have a formal group law over any other ring, then we have a homomorphism of rings and a map of formal groups from the universal formal group over the Lazar ring to this formal group which we have over an arbitrary ring. So how do we classify such formal groups in general? Well, we do this by means of a certain quotient stack. So let me describe a construction which classifies formal groups. So we start off with some spectrum. Then we take its cobordism ring, and then this ring, this thing here can be considered as a module over the Lazar ring. So it's a null module. And therefore, we can think of this mu of x as a quasi-coherent sheaf over the spectrum of the Lazar ring. And so this quasi-coherent sheaf admits an action of an affine algebraic group, which is the spectrum of this thing. So if we have a commutative ring, then the value of this algebraic group on this ring is all series in one variable over t, such that g of t is equal to t plus p1 t squared, etc. And so the action of this g on the sheaf mu of x is compatible with the action on the base space that is the spectrum of the Lazar ring, and this action is performed by means of the following construction. So if we have an element of this group and we have certain formal group law over R, this means that this pair is mapped to the following adjoint element in the set of formal group laws over R. So we take G minus 1 on the variables and then apply G outside. And we obtain another formal group law over R. Then basically we can basically we can interpret the Adams-Novikov spectral sequence in terms of this action on this quasi-coherent sheaf. So assume that X is a connective spectrum, which I guess means that we have trivial homotopy groups in negative dimensions. And then we can construct a homological spectral sequence which converges to certain, its infinity page is adjacent to homotopy groups of the spectrum, and E2 page of this spectral sequence can be calculated as cohomology groups of this group G with coefficients in the cobordism module of our spectrum. Another way to think of this E2 page is to think of cohomology of the quotient stack, which is denoted by this MSFG with coefficients in the sheaf Fx, where the sheaf Fx comes from this cobordism sheaf, and this quotient stack is just the factor, is a quotient of the spectrum of the Lazar ring by the action of G. So let's refine this statement a little bit. So this is one way to understand the Adams-Novikov spectral sequence, but we can make it even more precise if we think of the following pictures. So the Lazar ring and this ring of polynomials and countably many variables are naturally z-graded. And as is well known, z-gradients bijectively correspond to actions of the torus. So this means that we have an action of GM, both on the Lazar ring and on this other ring. So how this action works? Well, it works absolutely the same as the action of the group G. So the pair lambda F, where lambda is an element of the group of invertibles and F is some formal group law, is mapped to lambda F lambda minus 1 lambda minus 1. So this gives us the notion that actually this action of GM and action of G can be combined into action of a slightly larger group, which is denoted by G plus. And G plus for any commutative ring R consists of series in one variable such that well, we have the following series with one additional assumption, that is that B0 should be invertible. So, well, the torus lies inside of this series just as constants, and the group G is just as before. So we have a semi-direct product of the torus and the group G, and that's the group G plus. And so actually we can then consider another quotient stack, which is denoted just by M of G, which is the quotient of the spectrum of the Lazarov by the action of G plus. And this step is called the step of formal group laws. So if we have mu of x for an arbitrary spectrum x, then it is a graded L module, just as before. But actually, we can observe that if we take the even part of this module, which consists of the sum of all components of even degree, then it has a natural action of G plus compatible with action on the base. And this means that this mu even can be considered a quasi-coherent sheaf on the quotient stack M of G. And basically, then our analysis of various cohomology theories becomes an analysis of this stack M of G. So we will try to understand a certain stratification of M of G and see how, in particular, morality theories arise from this stratification. So let's try to understand some very basic properties of M of G. And we start from the following observation. So assume that we have a commutative ring R, and we have a certain formal group law over this ring, and assume that Log R is the category of R algebras. So to each formal group law over R, we can associate a functor GF, which goes from category of algebras to the category of abelian groups. And it works like this. So we take an algebra, and we take the set of all nilpotent elements inside of this algebra. And we have a group structure on the set of nilpotent elements given by the following multiplication. So since all elements are nilpotent, this formal power series reduces to some polynomial for fixed A and B, and this means that this expression makes sense. So this GF is then the formal group associated to the formal group law F. And now we can try to understand. We can try to understand what sorts of formal groups are out there. So basically, these formal groups which appear from formal group laws are, in a sense, the trivial kind. And of course, there are some other formal groups which are just functors from algebras to abelian groups. Let me discuss this category of formal groups in more detail. So assume that we have two formal group laws over R, and assume that we have an isomorphism between the corresponding formal groups. So this means that for each R algebra, we have an isomorphism between we have an endomorphism of a set of nilpotent elements inside of A. Let's denote it like this. And then alpha I induces an endomorphism. So to try and understand this endomorphism, it's useful to consider the universal case of an algebra with a nilpotent element, namely a truncated algebra of polynomials over the base ring, which has this element of degree of nilpotence n, which corresponds to the variable. And then we know that alpha A of t in this case is just some polynomial in t of degree n, or well, maybe smaller degree, but of course not above n. And it of course has no constants because the element should be still nilpotent. So since alpha is factorial, we actually see that these coefficients, so BIs, are independent of A. So they are actually an invariant of this isomorphism alpha, and they're the same for all algebras. And actually, by considering an inductive limit, if you want to, we see that actually it is not important that we consider just elements of degree n. We can consider elements of any degree of nilpotence, and we see that to each isomorphism we actually associate a countable number of coefficients which correspond to the way that nilpotent elements are mapped by this isomorphism alpha. So this means that to each isomorphism alpha, we actually associate a series G, and we have the following formulas. So f prime of G x G y is equal to G f x y. So this isomorphism between formal group laws which come from formal groups which come from formal group laws are just a series in one variable, and since alpha is invertible, G should be an invertible series. So now let me state what I was hinting at about the fact that formal groups which come from formal group laws are the simplest. Assume that we have a commutative ring R, then a coordinatizable formal group law, formal group over R is a functor G from R algebras to abelian groups, such that G is isomorphic to G of F for some formal group law F. And so we can consider a subcategory of formal groups, which is isomorphic to the category of formal group laws with morphisms being isomorphisms inside of the category of all possible formal groups. So we'll have this subcategory of coordinatizable formal groups where objects are up to isomorphism. GFs for formal group laws over R, and morphisms are invertible series so like this invertible series in one variable, which are morphisms, well, isomorphisms between such formal groups. So if we have just an arbitrary functor G from our algebras to abelian groups, we say that this formal group if first of all G is a sheaf with respect to Zariski topology on on the category which is dual to our algebras, so our schemes, and in plain terms it means that if we have two elements x and y inside of an R algebra A, such that their sum is a unit, it means that G of A is actually the equalizer of the following morphisms. So take the localization in both of these elements, we take the product and we map it into we take the product of values over two different localizations and map it into the localization in both elements. And this should be the equalizer of these two morphisms should be our group G of A. So that's just the shift condition. And another thing is that G is, so to speak, locally trivial. So G is coordinatizable. It's locally coordinatizable in the risky topology. This means that one can choose R1, etc., Rn inside of R, such that inside of sorry.
Grisha, I think there's something with your internet. You're like freezing up
There
in your.
seems to be a problem. Yeah.
Yeah, okay. Let me try to.
Yeah, can you please
fix
explain
this.
again?
Yeah, just one moment. I'll try to change my connection.
Yep.
Okay, so let me explain again. So the first thing is that this functor should be a sheaf on the category of R schemes, so the opposite category of R algebras. And I just spelled it out that it should be an equalizer. The value on an algebra should be an equalizer of the following pair of morphisms. And another thing is that G should be locally coordinatizable, meaning that we sort of, so basically we can cover the spectrum of R by an open subsets which correspond to complements of, well, hypersurfaces defined by these elements. And for each of these open subsets, the restriction of G to this open subset should be isomorphic to a coordinatizable formal group. So Fi should be an element of formal group laws over the localized string. So that's the definition of not necessarily a coordinatizable formal group over R. And now, basically by definition, the modular stack of formal groups MFG is a functor which assigns to each commutative ring R the category of formal groups over this ring. So it's the category of such functors with morphisms being isomorphisms. And we have a canonical map of stacks, which is a principal fibration with the fiber GM. So let's try and understand how formal groups can be non-coordinatizable. To do this, let's introduce the following concept, which is quite well known from general theory of algebraic groups. So assume that G is a formal group over R. Then the Lie algebra of G is the kernel of the following morphism. So we take the tangent bundle of this group, which is just this group considered over the dual numbers, and we map it to the usual group over R, and what we obtain is called the Lie algebra of this formal group. So if the group is coordinatizable, then the Lie algebra of this formal group is canonically isomorphic to the ground ring as an R module. So how do we obtain this? Well, this quite straightforward to see that G is actually isomorphic to R of t modulo t square, which is isomorphic to R. That's just because any formal group law when we mod out by monomials of degree at least 2 reduces just the trivial group law, and this shows that we have such an isomorphism. So obviously, if we have any constant inside of the ground ring, then we can define a morphism like this, which extends to the morphism of rings, well, to an endomorphism of this ring, which means that we have a group homomorphism from G to G. And this means that G is actually not only an abelian group, but as I said, an R module. Okay, so if G is coordinatizable, this action is compatible with this isomorphism. So this corresponds just to the usual R module structure of we see that locally for Zariski topology on Alk of R, G is isomorphic to R. So basically what we will arrive at is that this Lie algebra of a formal group forms a line bundle over, well, over this site, if you will. So this thing is locally isomorphic to R, and this means that G is an invertible R module. That is a line bundle over the spectrum of R. So now we have the following proposition, which gives a criterion when a group is coordinatizable or, in a sense, trivial. So a formal group over R is coordinatizable if and only if G is globally trivial, meaning that it is isomorphic to R. And the second part is that this quotient stack MSFG parameterizes pairs G alpha, where G is a formal group over R, and alpha is a trivialization of its Lie algebra. Okay, I'm not sure that we need to prove of it right now, but it's fairly straightforward to do that. So, well, I don't know. I mean, it's not that hard. I think that the main idea here is that basically we can trivialize. Basically, the hardest part is to show that if Lie algebra trivializes, that means that we can actually trivialize or coordinatize the whole group. And the key idea here is to show that the abstraction to such gluing of local trivialization vanishes because there are no non-trivial cohomology classes in the following cohomology group, because this group G, which was described earlier, is an iterated extension of the additive group, which has no higher cohomology on affine schemes. So this means that we can actually recover a coordinatization of formal group from trivialization of its Lie algebra. Extension. So this is trivial. Okay, so now we can think of this pair, and we can assign to it the inverse of its Lie algebra as an invertible module. And so this thing here is a line bundle omega over the quotient stack. And so MSFG then is just the total space of omega without the zero section. And this explains why there is this principal bundle structure of MSFG over M of G. And so now we arrive to the promised refinement of the result about Adams-Navier spectral sequence, namely that if we have some spectrum X, then we can take the even part of its cobordism module, which is a module of the Lazar ring, which this module structure is compatible with the action of the group G plus on the Lazar ring. And therefore we have a sheaf F even on the quotient stack M of G. And now the E2 page of Adams-Navier spectral sequence can be described using the two following cases. So we take for even first coordinate, we take HB of M of G with coefficients in F even tensor, this line bundle described earlier, to the tensor power of A. And for odd first coordinate, we take HB of the same quotient stack, but this time with coefficients in the odd part of this sheaf. And tensor it with the same line bundle. Okay, so now we have some understanding of the way this Adams-Novikov spectral sequence is related to this stack business that we described earlier. But now we want to study this stack M of G in more details. And to do this, we want to introduce a certain stratification of the stack, which is done in no small part by means of the notion of a height of a formal group. So let's first of all recall the following result about formal groups in characteristic 0. So assume that R is a ring in characteristic 0. Then for any formal group law over this ring, we can sort of represent it in a canonical form, meaning that each formal group law over the ring of characteristic 0 is obtained from the standard one or from the trivial one by change of coordinates. So we have an invertible series in one variable such that G of t such that f of x y is the same as g of g minus 1 of x plus g minus 1 of y. So as you can see, we have this trivial formal group law here, and we obtain our f by just change of variables. This in particular means that over Q, all formal group laws are trivial. So we have this statement that if we take the stack of this bundle over the stack of formal group laws and tensor it, take the product over the integers with the spectrum of rationals, then we just obtain the spectrum of rationals itself. And similarly, if we take the proper stack of formal group laws and take the product with the spectrum of rationals, then we obtain the classifying stack of the torus over the rationals. So this means that over the rationals, every formal group is completely determined up to unique isomorphism by its D algebra. So the simplest example, I guess, is that if we take the formal group law, which corresponds to ordinary cohomology, we see that it can be trivialized using the following series. So we take this ET minus 1, which is just the series of the following form. And it can be easily verified that then it trivializes the law F. Okay, so we see that the coefficients of the series are obviously not integral, and this suggests the idea that over rings which have positive characteristic, it can be in fact case that the additive and multiplicative group laws are not asymmetric. So let's see how this happens. And first of all, we need the notion of an endomorphism of formal group laws. So assume that we have a formal group law over R. Then we say that that a series one variable is an endomorphism of F if and only if well, the familiar condition which we had earlier for isomorphisms holds for G. However, now we don't require G to be necessarily invertible. So to prove this statement that any formal group law over a ring of characteristic 0 can be trivialized, we need the following notion. So we need the notion of translation invariant differential. So this translation invariant differential will be obviously something that lives on the formal spectrum of the ring of series in one variable. So first of all, let's formally introduce the notion of a ring of of a module of differentials, and that's just a free module over the ring of series generated by this symbol dt. And then if we have a differential gt dt, then we can act on it by applying to it an action of the formal group or of the formal group law. So we take f upper star gt dt to be by definition g of xy df dx so that's now a differential on the formal spectrum of power series in two variables. So now it's a module of rank 2 generated by dx and dy. And now we say that gt dt is translation invariant if upon applying this pullback map of this formal group, we obtain basically the same differential, but in each coordinate. So for the additive group law, a translation invariant differential is just the usual, well, the trivial differential dt. And if we take the multiplicative law, then we have the following translation invariant differential. So that's dt divided by 1 plus t. And it's translation invariant with respect to x plus y, x, y. Okay, so it can be seen that there exists a unique translation invariant differential, and it can be chosen as the basis element of the module of differentials. Okay, so suppose that we have a series which has no free term, so it's an element of this module. Then we can define a pullback with respect to this series of a differential, which is just given by taking the composition of G and H, plugging T in, and multiplying it by DH, where DH is defined by the usual rules of differentiation, meaning that here we have A1 dt, A2 t dt, etc. And this means that H upper star is 0 if and only if I is equal to 0. If P is equal to 0 in R, so R has characteristic P, this is equivalent to the requirement that AI is equal to 0 for I not divisible by P. And another way to state this is that H upper star 0 is H upper star is 0 if and only if it can be H can be actually represented as another power series in which we plugged in the polynomial Tp. So we sort of are mimicking the way we deal with extensions of fields of characteristic P here, and the way the irreducible polynomials over such fields can be obtained. So suppose that we have two formal group laws over the ring R, and suppose that we have a morphism between these formal group laws. Then H upper star maps invariant differentials of F upper star to invariant differentials of f. This means that if we had an invariant differential with respect to f upper star, then by applying h upper star, invariant differential with respect to f prime, we apply h upper star and we obtain some other invariant differential with respect to f, but since it is unique up to multiplication by a constant, is actually a multiple of this omega f. And this means that ht is equivalent to lambda t modulo t squared. So we have the following result. Assume that f and f prime are two formal group laws, and assume that R is a ring of characteristic P, and assume that we have a certain morphism between f and f prime, then we have one of the following. So either ht has the form lambda t plus something which is divisible by t squared, where lambda is non-zero. And the other possibility is that actually ht can be represented as this h prime of tp. Okay. So that's what follows from the previous discussion. And now let's define the sort of Frobenius homomorphism on formal group laws. So define Fp of xpyp to be fxy to the power of p. So in the second case of this statement, we obtain the following. So f prime of h prime xp h prime yp should be equal to f prime of h of x, h of y, and should be equal to h of fxy, which is by assumption the same as h prime of fp spyp. Which means that actually this morphism h prime defines, so the series h prime defines a morphism from fp to f prime. So by iterating the statement for several iterating several times, we arrive at the following result. So assume that we have a commutative ring R. Such that its characteristic is equal to P, and assume that we have two formal group laws of this ring. And assume that we have a morphism between them. Then there exists a certain non-negative integer such that h is equal to h prime of t to the power t to the power n, where h prime is of the form from the first part of the previous statement. So lambda is non-zero. Okay, so now let's define a special kind of power series in one variable, which will allow us to measure the height of formal group law. So assume that we have a formal group law over commutative ring. Then for any non-negative integer, we define a series n of t by means of the following recursive formulas. So if n is equal to 0, then n is the 0 series, and if n is greater than 0, then to obtain n of t, we should just plug n minus 1 of t and t into the series. So it is quite clear that this family of series defines a family of endomorphisms of this formal group law. And so also from the definition, well, it can be immediately seen recursively that n of t has the following form. So the first coefficient is precisely n. And so if R has characteristic P, it means that n of t has no linear part for n divisible by p. And so we can write p of t as c ck plus o tk plus 1. And so we obtain the following result. So assume that we have a commutative ring of characteristic P, and assume that F is a formal group law over R. Then either P of t is 0 or P of t is of the form lambda TPN plus O TPN plus 1 for some strictly positive integer. And so now we can define what is the height of formal group law. So if F is a formal group law over R, and P is some prime number, then denote by Vn the coefficient of TPM in this power series, and we say that F has at least n if Vi is equal to 0 for I less than n, and we say that height of F with respect to P is exactly n if in addition to it being at least n, Vn should be also invertible. Okay, so now the idea is that this height function basically determines stratification of the step M of G. I think that I've talked for long enough, so I will try to conclude as fast as I can. And so the idea behind Moravec theories is that they correspond to formal group laws which are sort of unique formal group. So we have this family of key theories for each prime, and basically they correspond to sort of unique group laws which have height n with respect to some fixed prime. I'm not sure that that's well, that's not very satisfactory description, I have to admit, because doesn't really show much of I don't know, the nature of this well, this object. But the idea is as follows. So we have this stratification of the stack of formal group laws, and we just say that Moravec theories correspond to very, very specific group laws which have fixed height with respect to chosen prime. I don't know, maybe maybe just to conclude all this, I will state that if we compute the homotopy groups of such spectrum, we obtain the following isomorphism. So this is Moravec theory of, I guess, P10 with respect to P. Then this should be isomorphic to the following ring, where this variable Vn quite expectedly is of degree 2 Pn minus 1. Okay, so I'm sorry, I skipped through a lot of stuff at the end, but I think that it's good place to stop. Are there any questions or comments?
Okay, so thanks. Let's thank Richard for the talk, and maybe I can stop the recording.